Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video. All math basic course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we jump into section 3.7, the last section in chapter 3 of the Big Ideas Math Integrated Math 2 textbook on comparing linear, exponential, and quadratic functions. This has been an entire chapter on quadratic functions where we've graph them every which way using any which form. Now we're going to get into the mix of using some of the linear and exponential and say, how do they all really compare to each other? We're going to be just looking at them, asking them what kind of model we have for each of them, and we're going to be comparing things with data. That's generally what comes in these sections. Honestly, generally we skip these sections when we're teaching them, at least from the schools that I've done them in. But you know what, if your school does it or if you're intrigued by them, this is for you. So go ahead and check out the description section down below, and you'll download this PDF if you'd like to, where I'm going to start with the lecture portion. And then if you want to follow the timestamps and find the problem set for the solution guide stuff, you can find that as well. I believe we go up to problem number 45. If you want to find other stuff within my playlist of the Big Ideas Math Integrated Math 2 textbook, you can go ahead and find that playlist, again, down below in the description section. Without further ado, guys, let's go ahead and get started. We might have to use a calculator when it hits things with exponentials, so just get ready for that. I don't actually know. I haven't done the problems yet. What you'll learn, you'll choose functions to model. You'll choose functions to model data. So are you choosing linear, exponential, or quadratic based on the data that you have? Write functions to model data and come up with them based on the kind of function you're going to use, and compare functions using average rates of change. Average rate of change is a fancy word for slope, but not all of our things will be linear, like this one here. We'll also have exponential and quadratic functions. So over an interval of a certain amount of x's, you can also still draw a line from there and figure out what that slope is. That's a previous term as well as slope. They really do mean the same thing overall. All right, choosing functions to model data. So far, you have studied all of linear, exponential, and quadratic functions. Quadratic most recently, you can use these functions to model data. Linear function is a straight line. You get y equals mx plus b as its general form. Exponential, we've only used y equals ab to the x. No real horizontal, vertical translation kinds of things. If we have to use them, I suppose we will. But they've been pretty good at making problems just like this, even positive ones. And if we use real world problems, like real life application problems, they'll probably also still be positive. And quadratic functions, we've seen every which way when they're two x-intercepts, 1 or 0, vertex form. This is standard form, but vertex form, intercept form, standard form, things like that. They all have different behaviors for sure, even though both of these curve, you know, one's a U shape, one is not. This one actually, over time, increases significantly more than a quadratic, which is something they'll probably talk about at some point. Using graphs to identify functions, if they ask you to plot the points, awesome. I just realized we're going to have to do a lot of things with graphs, probably, and hopefully they stay within a good scale like this, but plot the points, tell whether they appear to be linear, exponential, or quadratic. These appear to be quadratic. They don't say explain why, but we got the U-shape, linear, following a straight line, exponential, curved, but not U-shaped. And there is a constant common ratio here as you appear to be doubling each time. I guess I can mention that. That's what exponential functions will do. So they'll probably, because that's an example, they generally follow the example, so we're probably going to have to also draw graphs with them. Let me move myself over here. Let's look at differences and ratios of functions. Yeah, this is an interesting bit. You can use patterns between consecutive data points to determine which type of function models the data. The differences of consecutive y values are called first differences. Differences of consecutive first differences are called second differences. I guess I'll show you what that means visually. I've never called them that. I say the difference of the difference, so I'll try and call them first differences and second differences. When they say consecutive data, they mean when like x is like 0, 1, 2, 3, 4, like that, and then how the y values change. You can use these to determine whether it's linear, exponential, or quadratic. How? Linear function, the first differences are constant. So when, you know, the slope, you're adding 3 each time x increases by 1, that's a constant rate of change of adding 3. So up 3 over 1 is your slope. That's what a linear function will do. Exponential doesn't have a constant rate of change, neither does quadratic, but it's not something through subtraction or addition that we figure out. It actually has a common ratio, something you probably learned through geometric sequences, whether in IM1 or IM2, that you're multiplying by a number over and over. So we'll recognize that for its own thing. If we are trying to test out, oh, there's no common difference, do they have a common ratio? We'll go for that. The second differences are constant in a quadratic function, which is something that I hope that they really do show pretty, you know, visually and represent. We're clearly going to be doing that when we do problems. But yeah, quadratic functions, well, we'll see some examples in In all cases, the differences of consecutive x values needs to be constant. So, like I said, it could be 0, 1, 2, 3, 4, 5, but it could be 0, 2, 4, 6, 8, 10. It could be a constant like that. I hope they tend to just change them by 1, because otherwise we have to spend more time talking about the actual slope with that. And when it's a y value change, when it's a quadratic, it might be, or an exponential might be a little bit harder to talk about. These ones increase by 1, although they don't start from 0. Tell whether each table of values represents linear, exponential, or quadratic. In the first one, part A, and they show actually the visual here, you see as x increases by 1, a constant consecutive amount each time, the y's are decreasing by 3 each time. Those are first differences of -3. Therefore, that would be a linear function with first differences of -3. On part B, you can see that you add 1, and then you add 2, and then you add 4, and then you add 8. Not a constant common difference, but to the wiser, you will determine that you are multiplying by 2 there, which is a common ratio. A common ratio would be represented in an exponential function. And then this one is likely a quadratic. Yep, it is. So take a look at this. You're subtracting 1, then adding 1, then adding 3, then adding 5. I'm sure you could tell me what happens next in the pattern. +7, +9, +11, +13. You add the next odd number. But if we want to ask more about what's actually happening as an entirety within this thing, how I say it, the difference has a common difference. I think that's how I say it. The difference has a common difference. Even including the part of -1. From -1 to +1 to +3, +5, every number that you're adding is 2 more than the previous one before it. That's what quadratic functions do. They have a constant second difference, is how they say it. Constant second difference. So we know it's quadratic with that. We're not talking about cubic functions, but it's the third differences would have a constant as well. Is it always 2? No. It depends on the stretch factor of it. And I don't know if we're going to have to come up with equations. Well, we will. I don't know if we're going to have to come up with equations with different a values, but we'll check it out when it comes to it. So quadratic for the third. Doesn't look like they're going to ask you something, and it's none. None of them. So that'll be good. But otherwise, we use process of elimination to figure out that none of those apply. No constant first difference, second difference, or common ratio. Okay, writing a function to model the data. First, it looks like we have to tell whether it's linear, exponential, or quadratic, then write the function. We saw what kinds of functions they're using. Linear was slope-intercept form. Exponential was ab to the x. Quadratic was its standard form, ax squared plus bx plus c. So once we determine which one it is, we'll do something to make the equation off of it. This one shows the consecutive x values here, and something where we subtract 12, then subtract 4. Then we add 4, then we add 12. That's a clear-cut case of something that's probably quadratic, the fact that it bounces back up. And they show you right here that the second differences are constant. And it looks like they are going to change them instead of just from +2. They have a +8 going on. So what do they do? They use intercept form, and I have different thoughts on what we could do on some of these, because this to me is clearly the vertex as well. If I used vertex form, I think we could also come up with it. So I'll show you kind of what I could have done. But they use intercept or factored form here. They show the factors because the y values are 0. These are the x values for which y is 0. So x minus 1 and x minus 3 are your factors in this. But we got to find the a value that's represented here. And that +8 is very kind of determining of what it's going to be. That doesn't mean it's 8, but it's very determining of what's going to be. So choose a point that's not one of the, it's not one of those. Looks like they chose 0 for x, 12 for y. And then they do enough work, multiply -1 with -3, divide that 3, they get the a is 4. So they write out factored form to start off with, and then they go and distribute through foiling. They get this equation. So it looks like we're going to do standard form equations. Now, what could have I done? As I've spoken a lot through this chapter, I've identified how stretch factors work in a lot of ways. X is increasing by 1. This is +4. And then this is +16, right? Instead of 1, 1, 2, 4, it's 1, 4, 2, 16. You're taking your 1 squared and quadrupling it, your 2 squared and quadrupling it. So I could have told you from the jump, I suppose, that this was going to be an a value of 4, in which case you could have used also vertex form. 4 times x minus 2 quantity squared, and then -4. The vertex is clearly at 2, 4 when it comes to symmetry. So if I wanted to go from there, furthermore, I could have went ahead and expanded that and then distributed. I'm not saying this is easier, harder, or anything like that. I'm just stating that here's another version of what could have happened. Obviously, this was just an example that they said. So they chose factored form out of that one. So we'll see what's most beneficial for us based on the problem. If the examples lead by this and it keeps doing this, maybe we have to stick with that. But you can see these are the same. These are identical here. Okay. Previously, you wrote recursive rules for linear and exponential functions. I don't even know if I remember that. You can use the pattern in the first differences to write recursive rules for quadratic functions. So write a recursive rule. I don't know if I've done that. Write a recursive rule for the quadratic function f in example 3. Okay, so example 3, so we got to use the table or this. Let's see. For the quadratic function f. Let's see what they said. An expression for the nth term of the sequence of first differences is negative 12 plus 8. We probably got to use the table. So with the numbers here, 12, 0, negative 4, 0, and 12, they say starting from negative 12, you're adding 8 each time. They said that the first differences has a rule that is from negative 12, you're adding 8 n minus 1 times. This is something out of arithmetic sequences you'd kind of know how to do here. First term, common difference, but they're doing it from the first differences because the first differences has a constant, so we can build an arithmetic sequence out of that. Remember, negative 12 is the first difference, literally, that they had. And then they simplify that to 8n minus 20. So they distribute the 8 to 8 minus 8, 8n minus 8, and negative 12 minus 8 is negative 20. Notice that f of n minus f of n minus 1 equals 8n minus 20. So any term minus the one before it, 0 minus 12, or negative 4 minus 0, or 0 minus negative 4, 12 minus 0, would follow this rule for finding out what that difference of that value is based on what nth term you're talking about. So this is kind of a mix of explicit and recursive together then, because normally a recursive rule only refers to the term before it, which this technically does, but this also refers to the position of the term you're referring to. X in this case they're calling n, and they're kind of avoiding talking about the 0th term in this case. They're saying when n is 1, 2, 3, 4. So I'll have to try to remember to do that as well. I might have some issues doing it. I'll try my best. But it sounds like they're also using this n as well as f of n minus 1. So what do they say? If that's the thing here, when you add this thing over, then f of n is f of n minus 1 plus 8n minus 20. So yeah, what you would generally do for a recursive rule is take the value of the term before it and do something with it. We're used to, for arithmetic sequences, adding a common difference, for geometric sequences, multiplying by a common ratio. And there are lots of other versions of ones. Like I said, I haven't done many with quadratics before, so maybe this is kind of a new idea for me. I was thinking of maybe using both of the terms before it, but I don't know if I know how to do that, honestly. So if I follow kind of that plus common difference thing, you have to remember that this common difference in this case is not literally a common first difference, but a common second difference. And it looks like they're using this number to make that so, and that's why we're getting that equation. So that's the way that I think I'm going to remember it if we're doing it for a quadratic rule. If it's exponential or linear, it's going to be a lot easier to do. But the common difference isn't truly a common difference. The first difference has a common difference itself in the second difference, and we got to use that. So that's kind of interesting. I want to go ahead and, I'm glad they gave the example. I want to make sure that I follow that when I do the problems that we do. Okay, maybe lastly, because I know this was one of the last bullet points, comparing functions using average rates of change. I haven't seen any word problems yet. For nonlinear functions, well, okay, so I kind of said this. I'll just kind of give you layman's terms. They said for nonlinear functions, the rate of change is not constant, right? There's no constant slope like a linear function up 3 over 1 or something like that. It's always changing all the time, everywhere. So we sometimes use average rates of change to determine over time, on average, how something's happening. You're like, oh, my money increased, by this much over this period. So on average, it was, $20 a day. Even though it really wasn't. Maybe day 1 it was $1, and day 2 it was $2, and day 3 it was $4, and you keep doubling. But when you average over the course of time, you want to kind of give it to someone else. Just say, all right, on average, $20 a day, right? So what you do is you find the slope between those two sets of points. From this x value to this x value, there's a change of b minus a. That's the width. From this y value to this y value, there's a change of this y minus this y, f of b minus f of a. So average rate of change is slope. Don't let this formula confuse you, f of b minus f of a over b minus a. That's a y2 minus y1 over x2 minus x1. The change in y over change in x. And that's what we do to find those. I feel like I've done this before with y'all. It might be that because I'm recording this video out of sequence, it might be that it occurs in later chapters, in later sections. I don't actually know. So let's look at an example here using and interpreting average rates of change. The table, here's a word problem. The table and graph show the populations of two species of fish introduced into a lake. Compare the populations by calculating and interpreting the rates of change from year 0 to year 4. So from year 0 to 4, there's this set of species of fish here. And it's not linear itself, but we can find the average rate of change from here to here. We want to find out basically how much do you rise, how much do you run. That'll give us that slope. Sorry for not being perfect line there. But yeah, that's what we do. We take the difference from this population and this population. That's 428 minus 100 is 328. And from year 0 to year 4, that's 4 years. So 328 more species of fish. Graphs show the populations. 328 more fish over the course of 4 years averages to 82 more fish a year. What do they say next? Oh, that's species A. Species B. Oh, these are two different things. I gotcha. Species A is in a table. Species B is on the graph. Species B, year 0 looks like 100 fish, and year 4 looks like it has 300 fish. So that difference is 200 fish over the course of 4 years, and that's 50 fish per year on average. That's not what actually happened, but that's on average. And that's what they mentioned at this last part here. Species A is growing faster over the course of that time. Does that mean it does over the entirety of the time? No. These are two different exponential functions. I assume they're both exponential. And who knows? Oh, you know what? I don't know what this is. This may be linear. I didn't actually track what this is doing. But this one's exponential. This one may dominate it over time. I don't know. Okay, that wasn't the last thing. Comparing functions using average rates of change. As a and b increase, the average rate of change between x's a and b of an increasing exponential function will eventually exceed the average rate of change between b and the quadratic. Okay, so what they're saying here, and I mentioned this before, exponential functions dominate more than quadratic and linear functions. If I have a linear function like this and a quadratic function, doesn't matter that this one might be underneath for a little bit. Eventually, that curve is going to pass that thing. X squareds are going to dominate x's. Exponential functions even dominate quadratics. They both may be curved, and this may be curved as well and whatever, but this thing, the doubling effect. Doubling something that you doubled, etc. over time, an infinite amount of time, will absolutely take over squaring the next value and squaring the next value and things like that. Meaning the next, like when x is 9 and 10 or whatever, as opposed to doubling 9 times and 10 times, it exceeds it by a long shot. And that's what they're kind of saying here. Over time, exponential dominates. As a and b, so the average rate of change over time will grow more. So that's kind of what I was saying with this previous one. If this is a linear function here, I don't know. I'm not bothering tracking. It looks like it actually is. If this is a linear function here, it may beat it in the short run, but in the long run, when you compare these two, the average rate of change from year 0 to 10, I'm willing to bet exponential just flat out dominated it, or at least was getting close to. And once it does surpass it, it's gone. It's gone. Yeah, so that's what all this is saying. Exponential will dominate quadratic and linear. Quadratic will dominate linear. So compare different function types. Let x represent the number of years since 1900. The function boom represents the population of Cedar Ridge. That's quadratic. Pine Valley has a population of 50 people and increased by 9% per year. That sounds like it's exponential. Exponential, as we've written exponential models for these. From 1900 to 1950, which town's population had a greater average rate of change? Which town will eventually have a greater population? It's likely that the quadratic one, Cedar Ridge, I bet Cedar Ridge would win over this one here because they want to show you, early on it's good, but later on, look at Pine Valley. So what do they say? You plug in, average rate of change is what they go by. So you got to plug in year 50 and year 0, because 1950 is 50 years after since 1900. The model starts at year 0, year 1900. So what is the population in year 50? And it's over the course of 50 years. Average rate of change of 612 for Cedar Ridge. They are increasing on average. It's just an average. On average of 612 people per year over the course of the first 50 years. Whereas Pine Valley, about 73. You got to come up with this model first, with the 9% increase per year. 73 people per year on average over that time. Pine Valley is trickling. Cedar Ridge is dominating over the first 50 years. Over time, Pine Valley, and perfect. They're using a graph thing to show you this. Cedar Ridge was winning at some year. Looks like 1987. They met. They're the same. Pine Valley just made babies. People moved in, whatever it was. In 1987, at some point, they tied. After that, Pine Valley just dominates by the year, 1990. They're like, bye. And I don't know if it's a good thing to have overcrowded population, but you can see that it's just dominating over that time. So eventually, Cedar Ridge is going to win. Pine Valley is going to win. Okay, and that finishes the lecture portion, a very long one, 20 and a half minutes or so. So let's go ahead. This may be a long video as we have 45 problems. Let's see what's going on. Name 3 types of functions you can use to model data, describe the equation, and graph each type of function. Really, do all of that for this number 1 here. Okay, vocabulary and core concept check is getting us in. So there's linear, which is a y equals mx plus b kind of equation. It says describe it. It's linear. It has a straight line, a constant path, and then a graph for this would look like this. I'm going to fit this within this area, guys. I'm sorry if this isn't enough here. It's just the vocabulary and core concept check. Quadratic equation. It has when they say describe the equation, let's see. Name 3 types that you can use to describe the equation. I guess I could say the whole constant difference, and then constant first difference, constant second difference, all that kind of stuff. So I'll just say that out loud. Constant second difference in a quadratic equation with its model. That'll be some sort of U shape. It has a vertex. That's what this chapter was all about, quadratics. And then lastly, exponential. Probably should have saved quadratic for last. Exponential is the most dominant. Looks like we're using a lot of AB to the X stuff. Even that last word problem with the model stuff was the 9% increase. Was that? This thing dominates over time. It's got an asymptote. All that jazz. You remember that probably from chapter 1. This has a common ratio between consecutive terms. How can you decide whether to use a linear, exponential, or quadratic function to model a data set? Oh, that's probably the answer of what I was just saying previously. So whether to use one or the other to model, it depends on either based on the graph, see above, and or use the points to make a graph and observe its behavior, or determine whether consecutive inputs yield for linear functions a constant first difference. I'm going to have to get more room. It's going to stretch out here if that's okay. A constant first difference, a constant second difference in quadratic, or a constant ratio in exponential. I'll just end with that. Or do we use the word common? Common first difference, common second difference. I'll say common. I'm used to saying that personally. Oh, common stretches that out more. That's all right. Constant's good. All right, describe how to find the average rate of change y equals f of x between x equals a and x equals b. Simple. You find the difference in your y's over the difference in your x's. You calculate the slope. Calculate slope between them. So from a to b, that is going to be, I'll put equals, y2 minus y1, that's the y value at point b for x and the y value when x is a. y2 minus y1 over x2 minus x1. The x2 is b and x is a. It's a slope. It's a slope. I'll put m. Which graph does not belong with the other 3? Explain your reasoning. So I see 3 quadratics and an exponential. This exponential is actually not with an asymptote. Whoopsie. This exponential is actually not with an asymptote at the x-axis. It's actually at y equals 2. Interesting. We haven't seen that together as far as I'm concerned, but I mean, it happens. Get ready for that in IM2 for sure. But this one's exponential. It says explain your reasoning. That's an exponential one. The rest are U-shaped. Quadratic, and quadratic. There are, if you wanted to say, oh, these ones go upward, well, 2 of them go downward. If you want to say, oh, even the quadratics are all symmetrical across the y-axis, and this one's not, because it can't be. But there it is. All right, guys, I'm going to go ahead and get started with the problem set here. This is kind of a long time coming. We're almost 25 minutes into this thing, so without further ado, let's go ahead and take a look at what we're going to answer here today. Let's start with numbers 5 through 8, where we tell whether the points represent linear, exponential or quadratic function. They do not ask us to explain, so I will dare not to write an explanation, but I will just model what I'm seeing here. I'm sorry about that. This will be kind of tough to do with my mouse. Here, it's appearing. Listen, it's not linear and it's not exponential. Even if you wanted to argue it's a V shape or something, which it's not, a constant rate of change, that appears very quadratic on that one. Number 6 has an exponential set. I mean, given the points that we have, it appears exponential. Is there a case that it could possibly be quadratic? Yeah, maybe. But we don't see anything like that. They're not showing any of that behavior. I'm assuming these values are dividing by 2 each time. That's something that an exponential would do, and a quadratic would not. That one's exponential. Number 7. Number 7 also appears exponential. Again, it doesn't U when it's not straight. This thing's probably approaching the x-axis asymptote like that again. So also an exponential function. Let me draw out number 8 right now just to get you started so I don't have to go back and forth there. That looks linear, right? So 7 is also exponential. And then number 8 looks linear. It says appears to be. You know, we're not getting the exact values through calculation, and you can guarantee if these were on an answer key in the book or something like that, these are the answers you'd be getting. Okay, let's jump to numbers 9 through 14 where, they want us to actually plot the points, so I'll have to use graph stuff for it. I'll make sure to attach graph paper down below with all the stuff that we're doing here, so make sure you can download, print that, or use some of your own. But plot the points, tell whether the points appear to represent a linear, exponential, or quadratic function. And that's kind of what I was saying from that other set. If you look at the graph, you can tell yourself whether it's one or the other, which is what we just did. Or if you have the points, you can also plot them and make that same exact determination, or do the whole first difference, second difference kind of thing. So we got -2, because here's the thing. I don't know off the top of my head what these are, but they are going in consecutive order. -2, -1, -1, 0, 1, 2. Oh. And 2, 3. Well, what? And 0, 1. Oh, there's one in between. And 0, what? Oh, -1, 0. I put 0, 0. I said, what's going on? Now, these are out of order. That does appear linear. I'll go ahead and just state linear. So I don't have to connect the dots, right? If I can see what's going on with them, I'm just going to go ahead and call it out. Number 10. And the fact that they're showing fractions makes me think it's going to be exponential. And I'm not going to change the scale of any of the stuff here, but that's what it looks like. So 0, 1/4. What's the next one? -1, 1/16. Oh, definitely. I could even tell you what the equation is right now. 1, 1, 2, 4, 3, 16. 3/16 falls off of that, but you can see that shoot up thing. Man, exponentials really do what they do. Not quadratic. It's not U-shaping back. This is multiplying by 4 each time. This is very exponential. Hoping for a quadratic here soon. That's the headlining aspect of the chapter. That's something we came off of, but of course it's all about comparing them all. We just want to bring our baby back. So let's see if number 11 does exactly that. And there are ways, they do ask us to plot them, so I am. But I'm sure with just looking at them, we can make that determination without even saying the whole constant common difference stuff. I see fractions. It's not a guarantee it's exponential, but it's a good bet. 0, -3, 1, 0, 2, 9, -2, 9. So here's your U shape, right? This one, without drawing the graph, that is a quadratic. There's our baby. Without drawing the graph, you could say, well, I got symmetry. I have something going down and back up, but they're not written in order, so it's probably harder to notice. That's why it's probably good to also plot the graph. So let's go to number 12. I like that we're going fast to begin with. I doubt it's going to stay that way. Number 12. Oh, this is a 215. Remember, there was the other one that had 16. I have a tall graph. I'm going to go ahead and use that one. So -1, -3. -3, 5. 0, -1. Not linear, unless I'm plotting them wrong. 1, 5. Probably quadratic, right? And 2, 15. So despite its look, you're like, what the heck is that? What do I do there? The fact that it used back up says it's quadratic, at least if we have an option of only those three, or unless I plotted something wrong, but it looks correct. And, here's the thing. This is probably a vertex, which means there are probably some additional points like here that we didn't plot and here that we didn't plot, right? That's the whole idea. Do you see the quadratic now? Because I do. That's what will make this thing quadratic there. From what we have the clear-cut case of a vertex and all that kind of stuff. So they're really making you work for plotting the points to see what it is. Number 13, let me get the old graph back. We have, I don't know if it's just because I have decimals, makes me assume that it's going to be a thing. The fractions stood out a little differently before, so I don't know if it's going to be exponential. But -4, -4, -2, -3.4, my guess will be linear early on. -3.4 is right there. 0, -3, 2, -2.6. Yeah, linear. 4, -2. If you can tell, it's kind of an increase of what? 0.6 every time we change 2. I don't know what that slope is. 0.3. 0.3. That's linear. Appearance, at least, in what I see from that rate of change. And then number 14, maybe going back to exponential. Yeah, this is a different set of decimals that we see here. I'm going to guess probably exponential on this one. So number 14, we got 0.8, -4, and 0.25. You don't see that every day. -3.4. Yeah, that ain't linear. -2.1 and -1.3. Totes in my exponential book. Unless we're seeing any version of a curve in vertex, I ain't guessing quadratic. All right, numbers 15 through 18, we got to tell whether these represent linear, exponential, or quadratic functions. They don't ask us to explain, but I'm sure I'm going to, like, at least not in words, I'm sure I'm going to have to use some form of math things with them to judge for myself. I could probably say out loud what they are before we kind of make it happen. One thing I'm going to call out, if I notice right now, I'm going to look at all 4 of these questions and see if they do this way, is they always talk about a consecutive input values, right? So are these x's always changing by 1? That's what I just want to know. Yes, 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 yes. So we don't have to run into trickery. They're all increasing. They're in increasing order. They're always increasing by 1. So I'm not going to show this kind of thing every time, just this first time, that they add 1. So as we add 1 each time, what's happening to our y values? That's the question. This one appears to be a constant increase of 0.5 each time. And if it's that constant increase, first difference, this would be a linear function. They don't ask to write the equation. They don't ask to explain. I'll let that math concept speak for itself there. So that's going to be linear. On number 16, let's copy and paste that guy. Let me mute my volume every time I copy. I don't want that to show up. So that sound to pop up if you heard it. Number 16, again, constant increase with x, consecutive terms. This one here, not a constant increase here, +4, +20. But if you can see here, this is times 5 and times 5. Is the first one times 5? Yeah, 0.2 times 5 is also 1. With a constant common ratio of 5, you're talking about an exponential function on that one. Number 17. Looks like it's also exponential. Number 17. Looks like I'm multiplying by 3 each time. And by the way, if you were dividing by something over and over as well, that would count as exponential still. Because, like, say, dividing by 2, that's the same thing as multiplying by 1/2. So just kind of keep that in mind. You're still multiplying by something there. This one is also an exponential because of that constant rate. Exponential. And lastly, number 18, banking on quadratic, kind of hoping for one of those before we dive into the right equations of them. But on number 18, let's see if we got exactly that. Give me a second. 18. Okay. Am I seeing something where we're multiplying by the same amount? It's possible. Now, if you need to figure out what you're multiplying by each time, you would, 2 times 1 is 4.5. Even off the top of my head, I'm like, ugh, I gotta think on it. But if you wanted to figure out, you would do 4.5 divided by 2. What is 8 divided by 4.5? What is 12.5 divided by 8? The question is, are these the same? Are these the same values? Well, 4.5 divided by 2 is more than 2. I mean, it's 2 1/4, but it's more than 2. 8 divided by 4.5 is less than 2, so those aren't the same. This is getting even lesser than what that one was. This is not exponential. Not exponential. So where do we go from there? Well, is it linear? I think you might be able to see that it's not linear, but let's write out the first difference. We add 2.5, 3.5, then 4.5, and it looks like 5.5. So is it linear? No. But is there a constant second difference, right? Is there a common, does the difference have a common difference? That's the way I'm kind of used to saying it. We're adding one more than we did before. Even though they're 0.5s, we're adding one more than we did before, and that's the nature of a quadratic function. What's its equation? That would take a little bit more time to discover. Especially because, look, I don't see the vertex. I don't see any x-intercepts. Maybe they're not gearing us up to write an equation for that one. So that one would probably take a little bit more time to figure out. Based off the one, it's possible, but we'd have to talk about that a little more. We'll observe patterns over time. Number 19, our 5 through 18 must have been the nice ones. Now we're already hitting word problems. So we still have to go up to number 45, and I'm already 36 minutes in here. Modeling with mathematics. A student takes a subway to a public library. The table shows the distance in miles the student travels in t minutes. Let the time t represent independent. So kind of like your x and y. D is your dependent. Tell whether the data can be modeled by a linear, exponential, or quadratic function and explain. So let's just copy and paste the same thing. There's no difference in what we were doing before, except they want us to explain. I feel like I will still probably mostly explain in words, like speaking to you. But if typing something else fast, I'll do that as well. Let's go ahead and just try the common difference aspects first. Let's see if it's the others before exponential, so I don't waste my time with exponential also. This is not a consecutive difference here from 0.5 to 1. I'm going to do this. Notice how 1, 3, and 5 are consecutive. I'm going to gloss over this for a moment. I'm going to ignore that one because I don't want that to trick me in what I'm going to do. Let's see if this has a common difference to begin with from here. Note that this wouldn't be the slope because it's over 2. But if it's still a constant common difference, it works. 2.01 minus 0.67 is that difference between these values. That would be, I might have to use the calculator. That'll be, let me think of 201 minus 67, okay? Sorry about that. 134, so 1.34. And this is 3.35 minus 2.01. Is that 1.34? I think it is. 1.34. That's not a second difference, guys. That's the first difference there. Now, with this one here, this would have to own up and be the same kind of difference. Otherwise, it wouldn't work. But as you can tell, that's not 1.34. That's because this thing increases by only 0.5. That's 4 times less of an increase than this is. That means if I divide 1.34 divided by 4, I should get this difference as well. Let me check what 1.34 divided by 4 is. 1.34 divided by 4 is 0.335. Is 0.335 plus 0.335 0.67? Yeah, it is. So this is also 1.34 over 4. So it all checks out. That does make it linear. So it's linear because it has a constant, I'll just say, as they say it, first difference of 1.34. Okay. So we didn't really do much contextually with this. The 1.34, by the way, is what's time in minutes? Every 2 minutes. What was this about? Taking a subway? Every 2 minutes, the student traveled another 1.34 miles. Okay. Number 20. Another modeling with mathematics. A store sells custom circular rugs. The table shows the cost. I'm going to start copying this. The table shows the cost, C in dollars, of rugs that have diameters of d feet. Let the diameter d represent the independent variable. Tell whether, so same thing. Tell whether it's exponential, linear, all that kind of stuff. I don't want to balk at the fact that it might not, that it could possibly be linear. I'm going to start to see if it's exponential. I'm going to guess this looks like plus 50, then not plus 50 again. 50-ish and then not quite 50-ish. So probably not linear. Let's try in the exponential front. I'm going to check and see what if are we multiplying by the same thing here. What is 113.6 divided by 63.9? What is 177.5 divided by 113.6? I want to check those two first and see if they're the same. If they are, I'm going to assume exponential. If not, I'm just going to go and assume quadratic and move from there. So 113.6, because I don't know. 113.6 divided by 63.9 is this. It's a 1.7 repeating number. I'm just going to leave it at that. And then 177.5 divided by 113.6. Whoops, I typed it wrong. I typed 13.6. 113.6. Different number. So I'll show you on my calculator what I had there. First of all, I made a mistake. So I did this divided by that. I got 1.7 repeating. Then I screwed up in what I typed. Apologies. But I tried this divided by that. I got a different number. Not a common ratio. Likely not exponential. So I'm going to assume quadratic. Now I'm going to go for the differences. So let me do this with you guys here while I'm here. 113.6 minus 63.9. Let's get that difference. I'll go ahead and write it down. So that difference is 49.7. And then 177, these are just the numbers in the table. 177.5 minus 113.6. That difference is 63.9. And then 200, the next set, and this is a constant interval between. I didn't check that, but it is. 255.6 minus 177.5 is 78.1. My guess is this will be quadratic, and if so, that means these will have a constant, that the differences will have a constant difference, right? The whole thing here. So 49.7 plus what is 63.9? I think that's 14.2. So plus 4, this is plus by the way. Plus 14.2 here. Is this plus 14.2? Yeah, plus 14.2. That makes this a quadratic equation, quadratic model, because you have a constant second difference, constant second diff of 14.2. And that's kind of the reason behind that. All right. Number, I forget what the context of the problem is. Circular rugs. Numbers 21 to 26. Tell whether the data represents linear, exponential, or quadratic, then write the function. So now we're going one step further with this thing. The reason we have to tell it is so we know what kind of function to write. Whether or not they asked us to tell it, we got to know. So from the first set, and I apologize for not copying problems down earlier. That's generally a staple of mine to do so. I think because the first problems were graphs, I just kind of ignored the fact. And because I plotted the points on the next set, I didn't write them down. So I apologize. Most people probably don't care. It's just that's a constant thing of mine that I feel like I'm supposed to be doing. So I'll probably, for the tables, I'll probably still copy paste. Better yet, let's do this. Let's write them in a table. Let's do, so instead of copying down the numbers next time, I might just make the table immediately because I like to see the X's and Y's for what they are right next to each other. They are in order on X's, -2, -1, 0, 1, 2, 3, and it's consecutive. I have 8, 0, -4, -4, 0, 8. Automatically, I can tell you it's a quadratic. They don't ask us to explain why, but you can see the change from positive to negative back to positive. They don't show you the vertex. It's probably there's a clear symmetry between these, which means 0.5 is going to be the X value for the vertex, but we don't have the Y. So based on that, and based on not having that vertex, I couldn't even tell you stretch factor off the bat. So I'm going to do what they did before on this thing here. This is clearly quadratic. What I want to do is recognize the x-intercepts here. These are my x-intercepts, the value of x1, y equals 0. So we can come up with an equation, y equals sum a times x plus 1 times x minus 2. That's the factored form thing of what we have here. Because I don't need to say f of x, let's just say y. I need to plug in some x and some y that's not these ones. I'll go for 0, -4. So let's plug in -4 for y and 0 for x. 0 plus 1 is 1. 0 minus 2 is -2. Very easy. And solve for a. Find the a value based off that. Negative 2 times 1 times a is this, and divide by negative 2, you get a equals 2. So our equation can be written in this factored form with these values here. We can say 2 times x plus 1 times x minus 2. That's one answer. But they've been clearly showing you a little bit more of standard form. So let's go ahead and distribute this guy. It's 2 times x squared minus 2x plus 1x minus 2. And distribute the 2, you get 2x squared minus 2x minus 4. Now, I'm going to believe that answer because 0, negative 4 was indeed the y-intercept, right? That was the y value that we saw right here. So I'm going to trust that what I did was working. And there it is. Okay, let's go to number 22. Now, on number 22, as I said, I'm going to go straight into making a table out of it. Let's do straight like that. For x, y, how many points? 1, 2, 3, 4, 5. All right, so we have negative 3, negative 2, negative 1, 0, and 1. It's looking a little exponential. This is 8, 4, 2, 1, and 0.5. I am under the belief that, especially since there wasn't an example of an exponential or a linear, that we had done exponential equations in the past. And I'm going to dive right into it with you guys. It is exponential. It's exponential, as you can see. This is where you're dividing by 2, right? But you really want to say what you're multiplying by. You're multiplying by 1/2. You could also say 0.5. Dividing by 2 is multiplying by that. Whether you say 1/2 or 0.5 is going to be fine. So it's an exponential equation. This comes in y equals ab to the x form. Your a value is your y-intercept. It's the value of y when x equals 0. So for y equals ab to the x, the y value is 1. The b value is that growth rate that you have right there, the 1/2 to the x power. So I could also just say y equals 1/2 to the x power. That's all good. That's a version of the answer. If I use 0.5, all the same. Notice the a value now becomes kind of insignificant when it comes to writing the 1. The 1 isn't kind of really as needed to write there. Now I'm stressing this part here. I'm not required to put parentheses around this guy here, but I am required to put it around with fractions, in case you didn't know. Let's go to numbers 23 and 24, where we have tables, and I will be copying, pasting these ones in instead because it's there. So I'm a little lazy. 23. We have the earmarks of what is subtracting 3 each time, and I'll just go ahead and show what that is. That is going to make this a linear function. Linear. And if it's linear, let's write the equation in y equals mx plus b form. Y equals mx plus b means slope. That's what this is. As long as x is increasing by 1, that's the slope, rate of change there. Y-intercept is value of y when x equals 0. The y-intercept is going to be negative 2. So y equals negative 3x minus 2 is that equation. Stuff that you had child's play, stuff you would have done in IM1. Number 24, or whatever. Number 24, copy paste this guy. I'll take another 3 more linear equations. Don't mind if I do. Not going to be the case, but I'll take them if you're going to offer them, please. Constant increase of 1, whereas this thing looks to have a doubling effect, so times 2 each time. That'll make this thing exponential. It seems I have no rhyme or reason to what colors I use and when, so I'll probably just stick with black. Exponential equation, y equals ab to the x. When x is 0, y is 5. That will be the a value. That was the y-intercept. And doubling effect means 2. And there it is. Looks like the only harder ones to do are the quadratic ones, right? A little more work, unless they don't show the y-intercept straight up on some of these ones. We'll have to do a little more work then. Numbers 25 and 26 are graphs. They are visually there. I'll just let the visual be what it is because I wouldn't expect you to copy those down necessarily. So I won't. On number 25, it's clearly a quadratic, but we do need to come up with the equation. Now, I'm more keen on coming up with the equation based off ways that I've taught in this chapter if I have the vertex, and I'm going to be speaking on that right now. I'll speak on it instead of plugging anything in. The scale, these go by 2s. That means this is the point 1, 3, 1, 3, and this is clearly, negative 3. And this is clearly 2, negative 12, and then vice versa on the other side where we have a vertex at the origin. vertex at the origin. So when it comes to whether you say vertex form or standard form or anything like that, oh, this is still 25. This has a stretch factor of -3. So -3 ends x minus 0 squared plus 0. It's -3x squared. This is going, instead of 1, 1, 2, 4, it's 1, 3 to 12. 1 times 3, 4 times 3, and downward. So that's going to be the equation of this quadratic. And that's how I've been speaking on it before. I'll continue that here. Number 26 is clearly a linear equation. These ones are probably easiest to see the graphs to not only answer that, but answer the question as a whole. I have a y-intercept of -2, and as x increases by 1 each time, I'm going down 2. This is down 2 over 1, down 2 over 1. So a slope of -2. So y equals -2x, and the y-intercept is -2 as well, and that'll be my equation. So kind of fast at the end there, and I'm not mad. I hope you understood. Number 27 and 28. Write a recursive rule for the function represented by the table of values. Going to be curious when it hits a quadratic. Maybe it's looks like it's already starting with a quadratic. So let's see if I recall. I think I know how to do it, but let's see if I recall how I can say it to you guys. That if you have more questions, write them in the comments section down below and ask me about it. So it says by the functions, they don't tell you it's a quadratic. I can tell you it's a quadratic because we first subtract 1. In fact, I think we got to get these numbers out anyway. We subtract 1, then we add 1, then we add 3, then we add 5. What you're seeing is the second difference is constant, where 2 is added each time. Now, as 2 is added each time, that'll tell you it's quadratic. What we need to do is come up with the idea of what the first difference is doing as a whole. So the first difference has a rule. The rule is, remember, this is term 0. This is term 0, where we start with, I shouldn't say term 0 in this case. From term 0 to term 1, the first difference that we apply is with the -1. So starting from -1, we're adding 2 more than we did previously. So as n increases by 1, these x is also your n values. As n increases by 1, you're doing another +2. This is an arithmetic sequence thing. Looking at these numbers as a sequence, -1, 1, 3, 5, literally. Starting from the first term, add 2 more than what you did before. We're coming up with that rule. This isn't a common difference, but this is the difference's common difference. As they simplified it at the time, they would do distribution and combine like terms, and you get 2n minus 3. So this is, I'll just call this D. This is the constant common difference. Excuse me, this is the difference's common difference that we're using. This is what's making it do +2 each time. 2 more than before. So, as a whole, and I'll show you that this works here. As a whole, your rule is going to be to find a value, take the value before it, and add your common difference. And our common difference is going to be 2n minus 3. Which is recursive and explicit at the same time. But that would be the final answer there. So what does all that mean? It means this. If I want to find the value of the first term, I take the value of the 0th term and add 2 times 1 minus 3. So to find the first term, you take the 0th term, which is 2, and you add, what's 2 minus 3? You add -1, which means you subtract 1. And that value is 1. We get -1 to get 1 there. The first term is 1. All good. To find the second term, we take the value of the first term. We add 2 twice from -3. It's kind of weird to say that. So that'll be, let me kind of take this one out to see what we're looking at. The first term was 1, and we add 4 minus 3. We add 1, and we get 2. Is the second term 2? You betcha. Does that mean the third term's 3? No, it's 5. Let's see if we can get 5 from that. Last one I'll do. The third term, from the third term, you take the second term, and you add 2 3 times from -3, which means the second term being 2, we add 6 minus 3, we add 3 to it, and we get 5. So yeah, take the previous term and add 2 more than you did before with that rule, and that's going to follow it. And it looks like the last one will probably do the same thing. So that's number 27. Let's move to number 28. Next page. Number 28 Not quadratic this time, so it's not going to be a trickier one. What are they asking us to do? Come up with a recursive rule. So for this one, let's copy paste that. This one's a lot simpler. Oh, you know what I didn't put? Let me go back. You know what I didn't put was a recursive rule should also tell you what your first term is. Now, or let's say the 0th term. I even started from the 0th term as well. The 0th term is, because it's technically not a sequence, so you can have 0th terms. So 0th term was 2. So you need to express what the starting term is, otherwise that rule stuff doesn't make any sense. Where are you starting from? Okay, so this rule here, we're also starting from 0. Let's do that copy paste like I was about to do. This looks exponential as we are doubling each time, and that's really what the rule is going to be all about. Starting from 3, we're going to double what we did before. So times 2 happening there, that's a common ratio of 2. So when it comes to writing your rule, this whole f of n, take the previous term and do this thing to it. Our thing to it we're going to do is multiply by a common ratio. And that common ratio is going to be 2. So that's the answer. Now you start from 3. F of 0 equals 3. That's where you start from. So it's like this. To find the first term, you take the 0th term and 3, and you multiply by 2, you get 6. To find the second term, you take the first term of 6, multiply by 2 to get 12. Third term, take the second term of 12, multiply by 2 to get 24. Fourth term, take the third term of 24, multiply by 2 to get 48. That's how the recursive rule action works. Numbers 29 and 30, and I haven't ever had 3 error analyses questions, so I assume it's just those 2. On numbers 29 and 30, we are going to do error analysis. Describe and correct the error in determining whether the table represents a linear, exponential, or quadratic function. So they show a times 3 effect, and they state that it changes by a constant amount, so it's linear. It's changing by not a constant amount, but a constant ratio. So this function is so not linear. They are correct that the y values, that the consecutive y values, change by multiplying by 3, but that is not akin to a constant amount. Rather, it is a constant ratio. Therefore, it is exponential. Not linear. Not linear. I'll say not linear. Okay. Sorry about the spacing. I thought that thing was normally... it normally spaced itself out properly. All right, number 30. We do change it by a constant amount of 1. And then we see subtract 4, subtract 2, plus 0, plus 2. That all's good. That the second differences are plus 2. All that's good. The table's good. Table represents a quadratic function. X minus 2, x minus 1. So so they take the intercepts. Where are they? X minus 1 and x. This should say x plus 2. So I don't know if that's the only issue, but that should say a plus. Let's see if they do anything else wonky from there. They choose an xy of negative 3 for x and 4 for y. They negative 3 minus 2 is negative 5. Negative 3 minus 1 is negative 4. Negative 5 times negative 4 is 20. 4 divided by 20 is 1/5. So you get that. You distribute. You get x squared minus 3x plus 2. 1/5 x squared minus 3/5 x plus 2/5. Everything's good, but one exception. This should be a plus, which means it'll change this. It'll change things. It'll change a bunch of things, but they have one of the factors. So one of their factors is x minus 2 instead of x plus 2 for x plus 2 for the x-intercept. See, this spacing is normal. For the x-intercept of negative 2, 0. So let's fix it. Still probably going to have, I don't know if it'll have fraction implications anymore. We'll see how it changes. So f of x equals a times x plus 2 times x minus 1. I'll even substitute the same thing they did. I would have rather plugged in 1 and 0, but you know what? Let's just keep the same things otherwise. 4 equals a times, this is negative 3 plus 2 times negative 3 minus 1. And that is negative 1 times negative 4. So, all right, this will clean up a little bit better, which is great. So A is going to be 1 in this case. Okay. Now, if A is 1, our equation will now be able to say 1 times x plus 2 times x minus 1. That one is no bearing on what I'm going to do when I FOIL. So I'm going to get x squared minus x plus 2x is plus x minus 2. Like that. Okay. There's the change. Much better. It's still quadratic. But some other things change from it. Number 31, bottom of the page. The table shows the number of people attending the first 5 football games at a high school. The crowd's increasing. Oh, no, they go up, they go down. They change a little bit, and they go back up again. That's okay. Plot the points. Let the game G represent the independent variable. Because the scale is so bad, I'm just going to kind of like makeshift it. It's all first quadrant stuff. I got G as the independent. That means P is the independent. So game 1, 2, 3, 4, 5. No game 0 on this. We're going between like 200 and 300. So let's just go like 100, 200, 300, 400, etc. All right. Game 1 has 252. So about 250. Game 2 has 325. Sure. Game 3 goes back down to 270. They must have lost. Must not be playing a rival. I don't know what kind of stuff. Game 4, even lower. They're on a losing streak, folks. It's about the same as 252, so I'll just kind of make it look the same as. And then Game 5, last game of the season. They play about 10 games in high school, so I would believe if that's the last home game of the season. So 310. The Surge, close to 325. I'd say the 325 needs to go a little higher. Why? I'm trying to move. Oh, that's weird. Okay, well, I'll just kind of fill it out. It's okay. But this one here, I mean, I don't know what the next question is after this, but this doesn't look linear, exponential, or quadratic. Yeah, can a linear, exponential, quadratic function represent the situation? Explain. No, there's too much fluctuation in points here. There is too much oscillation. I'll say fluctuation. I'm sure you know that word better. Fluctuation in increasing and decreasing of values to be linear, exponential, or quadratic. Basically, it's not linear, it's not straight, it's not a U shape, and it doesn't have not a constant increase, but a progressive increase over time. It could be like a sine graph, sine, cosine, tangent, something like that. You haven't done any of that stuff in IM2, and you have to wait till IM3 till you do those, but there are ways to model those kinds, assuming it repeated that pattern. Who knows what that would do? Maybe there's a cubic function that would go off of that. Who knows? You have to see more games, larger sample size. Or maybe there's no model, right? Number 32. The table shows the breathing rates Y in liters of air per minute of a cyclist traveling at different speeds in miles per hour. So we do have consecutive increases on X, whereas the breathing on Y is there. Plot the points. Plot the points. Let X represent the independent, then determine the type of function that best represents the situation. Okay, well, I don't know how I want to plot this in terms of, do I want to cut off part of the window? Like, do I want to go from 0 is basically my question there. Because what I could do is I could make the window not go from 0 on Y to begin with. And then if I do that, I think that'll be more confusing. So I'll probably not do that. Let's just do what we can on it. I mean, when they ask you to do these things, I don't know what's specifically expected of, like, the book writers, your teacher, stuff like that. So here's the one I also don't like, are the X's. Because, look, this would be like, say this was 10 and 20 and 30, right? My points are all right here. 1, 2, 3, 4. They're all just like that. And then the 50, 60, 70, 80. Maybe I will do that thing where basically I'm not starting at 0 from either of these. This will be, for example, 20 and 21 and 22, 23, and 24. So we're not starting from 0. That means you can't assume these things are intercepts. I think they kind of do like a squiggly thing when they show that. They're like, okay, That's not starting from 0. Okay? So I'm going to say the same thing here. This goes from 50 to about 80. Let's see, 50, 55, 60, 65, 70, 75, 80. I'll do that. So 50, 55, 60, 65, 70, 75, 80. And then we'll kind of plot those points based on that. I guess that's the best way to go about this stuff. So we got X and Y. Okay. So the table shows the breathing rates of a cyclist traveling at different speeds. So the faster you go, the faster your breathing rate is. So at 20 miles per hour, you're at 51.4 liters of air per minute of breath. Remember, it's a rate. 21 miles per hour, 57.1. 22 miles per hour, 63.3. This looks linear-esque. We'll see if that's what it is. 23 miles per hour, 70.3. Oh, that looks a little larger. Maybe not. Oh, maybe not linear. This is interesting. 24 miles per hour, 78. If I were a betting man, because this isn't maybe perfectly scaled, right? I'm not doing everything the best I can. It says, determine the type of function that best represents the situation. Linear, as unscaled as my thing, linear, this does not appear to be. I would rather, and quadratic would probably also not, I bet this would be exponential. Now, when we, I don't know if they want to determine based off the visual, because that's normally what we would do. But check this out. This difference here is about 6. This difference here is about 6 as well, right? Not too. Actually, this one's less than 6. That one's more than 6. This one's 7. That one's more than 7. Closer to 8. That's increasing more over time as it goes. And that's kind of how it works for me when it comes to running or cycling or whatever. I kind of get more intense as I go there too. Just off these different speeds, it appears. So I'm going to venture a guess on exponential. I don't know how deep we want to go with quadratic with that. I might have to, it says write a function that models the data. Oh, geez. I don't want to go linear. I don't feel quadratic. See, I know the domain here starts at 20, but say it was quadratic, right? Say it was quadratic and we zoom this thing out. These are our points, right? I don't want this quadratic model to extrapolate itself and say, well, you would have breathed really fast if you ran 0 miles per hour. I'd rather this kind of, and assuming that they're smart about how they wrote the problem, I would rather that this faces more of an exponential flattening as we go on over time closer to 0 miles per hour. These are but parts of breathing rates within these aspects. I feel like exponential is what they're aiming for here. Now, for me to know for sure, they said write a model. Let's see what exponential does. Let's see if there's a constant common ratio. You know what? I didn't bother checking that. So I'm going to go to my calculator here. And I'll show you it. I'm going to go to the calculator, and I'm going to try these numbers in division. Let's try and do 57.1 divided by 51.4. There's a number. Let's do 63.3 divided by 57.1. Listen, they're not the same, but those are really close. They're close to about 11% increase. Let's see how close the next ones are, because I'm inclined to do this before quadratic personally. 63.3. They said that best represents, so I don't think there's an exact answer. This is destined to be exponential, guys. The fact that they couldn't get it exact is just because they rounded their values of what they used here before. This is clearly exponential. There's like an 11% increase each time when it comes to rounding. Hopefully you can see that. 1.11 is approximately the common ratio that we're doing here. So that's what I'm seeing here. I'm just going to put times 1.11 in that when I write my model, that's what I'm going to do. The next question, though, comes, how do I write my model when I don't have my y-intercept? There are answers to that. There are ways to do that. What I could also do is treat 20 like my y-intercept. I said before that it's not my y-intercept, but you can write a model that does that if you do a shift. And I don't know if you guys have seen shifts before. I think it would be too far out to do get the actual y-intercept unless you know clearly what you're doing with it. You got to divide by 1.11 20 times. which is easy. You use exponents for that. 51.4 divided by 1.11 raised to the 20th power. I don't see what this number is. 6.37. I don't know if that's what they're going with. I'm going to go with, well, listen, I'll give you two different options. One option for me will be this. And you don't know much about horizontal shifts for this stuff, but I'll tell you how it works and why it works. If I treated 20 as the y-intercept, truly as the y-intercept, that would mean that my initial value would be 51.4. Now, is it the true y-intercept? No. But what makes this 51.4 when x equals 20? If I'm raising my common ratio to the 0 power, what would make me raise it to the 0 power? If I did 20 minus 20. So if my x value started as 20 and I subtracted 20 from it, that would give me this as my new it's not my y-intercept, but it's my starting value that I use to get 0 when I plug in 20 for that. That could be an example of an answer. You can do that for any exponential function. We just haven't done much on horizontal shifts. The other version that you could do, and here's what I did in my calculator. I basically found what the y value would be if x was 0. If you divide, now remember 1.11 is approximated, so that's another reason I kind of don't want to do that. But if I divide by 1.11 20 times from the 20th term, see, to get to the 19th term, I got to divide by 1.11 once. 18th term, divide by it twice. 17th term, divide by it 3 times. The 10th term, divide by it 10 times. 20th term, or 0th term, divide by it 20 times. And that's what I did. And I get 6.375, around 6.4. So I could also say, if I round to the nearest 10th, y is 6.4 times 1.11 to the x power. Is that perfect, and will that get me the values I had before? No, I'm really rounding that number early. So there are a lot of reasons why I might not want to do that. I'm using a rounded number to get this. I'm rounding that early to get that. It'll be iffy. It'll be close, but it'll be iffy. So this or that, this one is better, preferred. I just don't know in either case if you know what to do on that. It's more of a challenging problem. It's more of a challenging problem because they didn't teach you it. But there it is. Find the there's a part C. Find the breathing rate of a cyclist traveling 18 miles per hour around your answer to the nearest 10th. So we have two different models to work off of that we can do that. The basic idea is you could divide by 1.11 twice, but we could also, this was part B and this was part A. We could also plug in 18 into either of these. So I'm more inclined to use the top one. Honestly, yeah, I'm more inclined to use the top one there. So 51.4 times 1.11 to the negative second power is basically what's going to happen. So I use the calculator for that, right? I do 51.4 times 1.11 to the negative second power. And we're getting 41.7. 41.7. What was this? Liters of air per minute. I'm going to show you the screen later. Of air per minute. You could probably put LPM or something like that. I want to try the other one where I would do 6.4. 6.4 times 1.11 to the 18th power. Let's see the difference here. This should be bigger because I rounded up to 6.4 from 6.37, etc. It's it's not that bad. This one would round about 41.9. That's not that bad. The other's 41.7. So it's not a terrible model. It's just not preferred. I think the other one's more accurate to what we're doing if 1.11 is accurate enough. So I put this answer here, 41.7 liters of air per minute. Anywhere close to that, 41.5, 42, I'm sure would be fine. We're using the model. Okay, let's move forward. Let's go to number 33. That was a pretty long question, especially because I had to discuss what I wanted to do. Analyzing rates of change. The function f of t, this problem doesn't seem any shorter. The function f of t equals that represents the height in feet of a volleyball t seconds after it is hit into the air. So let me copy that down first. Negative 16t squared. That's a gravity component, right? Seen a lot of those. Copy and complete the table. Copy. Don't mind if I do. Complete. Do you mind if I don't? Complete the table. I'm probably going to use my calculator, right? You can substitute things. I mean, I am going to use the calculator, but I'm probably going to use the this feature here. and kind of make the table thing and write it down from there. You can plug them in, obviously. This is fine, whatever we do. Just when in doubt, use your parentheses if you're doing it otherwise in a different way. So I'm going to start from 0. I'm going to increase by 0.5 if you saw what the table was. And I'm going to write down some of these numbers from 0 to 3. We're going to get 3. Are these exact? These must be exact here. Yeah, these are exacts. No rounding. 3, that's good. 23, 35, 39, 35. Oh, yeah, it's a quadratic. 23 and 3. It's very quadratic, if you know what I'm saying. So there's the table there. Letter A. Letter B. Plot the ordered pairs, and draw a smooth curve through the points. I'm going to use my tall graph feature. And I guess I got to scale by 2s. They say 39 as kind of the top point here. I don't need anything. Sorry about this. I don't need anything below the x-axis, so I think what I'm showing you here is fine. But what I do got to indicate and stress here is that this will be 5 and stuff. That's all good. Actually, these go by decimals. So let's do this. Every 2 of these is a 1. So we'll call this, I have kind of itchy nose syndrome right now. Little runny too. So 1, 2, 3, etc. I also don't need this. I don't need any of this stuff here. Let's just wipe that out. It's probably easier if I didn't go about it this way and just did what I did from the last problem. Just kind of wipe that out and wipe that out again. I'll go and write that again. So 1, 2, 3, 4. This will be 10 and 20 and 30. Ooh, that still won't fit the 40, 35 and stuff. I'll do the best I can. Okay. 1, 3. 2, 23. That's really shooting up, man. 2, 23. Oh, that's not 2. 2, 23. 3, 39. Oh, 3, excuse me. Oh, hold on a second. Hold on, this isn't 1. Let's do that again. 0.5, oh, 0, 3. What am I doing? 0, 3. Yelling at the screen. 0.5, 23. There we go. 1, 35. Now this is 34, so 35 would be halfway between that and the next increment. 1.5, 39. So 32, 34, 36, 38, probably 39. It's probably right next to that 39 right there. That's good. And then that's the symmetry. So right here at 2, we get 35. At 3, oh, excuse me, at 2.5. At 2.5, we get 23 again. So right there. And then at 3, we get back down. We actually don't even hit the 4. I could probably even wipe that out. Just kind of get rid of all that. So there's the graph. They did say plot a smooth curve. I mean, it's a quadratic. It always was. We knew the model. Curve ain't that great, but that side's a little. That side's not that good either. Describe where the function is increasing and decreasing. Well, it's increasing from, and here's part of the problem. This is what, a volleyball? What is this? A volleyball t seconds after it's hit into the air. It's increasing from, if I use interval notation, times 0. Sorry, I shouldn't put an arrow here because the domain starts at times 0. So at 0, 3 is where we begin. Now, did it say what happens at 3 after it's in the air? I don't know if it hits the ground or if it gets set at another 3 feet, but at best, it will hit the ground again just after 3 seconds. That's the only problem decreasing that I don't know for sure. Somewhere a little bit after 3, let's just say that. But including 0 all the way up to, and you could argue it's still, I mean, I don't make the argument, but to 1.5 is where it actually kind of stops increasing. And then it's decreasing from 1.5, not including it, all the way down to 3. I'm just going to go and include 3. I don't know what happens after 3. It's not very much time after that it would hit the ground. 3.08 seconds, something like that. So I'm just going to put it like that. That'll be kind of close enough to me. That's my description using interval notation. Those are times, by the way. Those are times. Part D. Find the average rate of change for each 0.5 second interval in the table. What do you notice about the average rates of change when the function's increasing and decreasing? So for average rates of change, listen, I'll just copy and paste this table one more time. Now that I have my values, we're just finding the slopes between these values. You're going to have a little bit of that curve in there. That's okay. So for this part D, it says average rates of change for each 0.5 second interval. So I want to find the slope here, the slope here, the slope here, etc. I don't know how to kind of do that best, but I do want to put it here. Notice how we're dividing by 0.5 each time, right? Dividing by 0.5 is the same as multiplying by 2, okay? So I'm going to say these, I'm going to work this one here the first time. 23 minus 3, which is 20, over 0.5 minus 0. That is 20 over 0.5, which is 20 times 2, which is 40. So that slope is 40. That is, this is feet. It's averaging 40 feet per second of kind of increase over the course of the first half second of this thing. Does it stay like that? No, gravity takes over. But that's the initial bump speed, 40 feet per second upward. From there, let's kind of work this out from here. 35 minus 23 is 12. Times 2, divided by 0.5, times 2. 12 times 2 is 24. 24 feet per second for the next half second, on average. And then, 4 times 2, 8 feet per second. And then negative 4 times 2, negative 8 feet per second. And then negative 12 times 2, negative 24 feet per second. And then this will be negative 40 feet per second in the same way that you saw before. So what did they ask? What do you notice about the average rates of change when the function's increasing? Function increasing. This is something you'll learn in calculus. Derivative positive. Function increasing means rate of change positive. Average rate of change positive. And function decreasing means average rate of change negative. You're also going to learn that about what's called instantaneous rate of change. When you do calculus, like 9 years from now, about 3 years from now, if you take calculus stuff, you'll learn that. But you're learning it now. That's what it means. Gotta unplug my ears. Okay, that is part D. We totally slowed down in the last two problems here. Way past the hour mark. Here we go. Number 34. Still, 12 questions to go and probably a lot more depth. Okay, analyzing relationships. The population of species A in 2010 was 100. The population of species A increased by 6% every year. All right, automatically I'm going to write a model. It's an exponential model. So right here for population A, I'll just say y sub A equals 100 for the initial population. This was year 2010. And then increase by 6% every year, 1.06 to the x power. We're going to use variable x just like the graph is using there. Let x represent number of years since 2010. There's a model. The graph shows the population of species B. Compare the populations of the species by calculating and interpreting the average rates of change from 2010 to 2016. So population B, which looks like a quadratic, I'm not going to be writing an equation for it, but I will be finding the average rate of change from here to year 6 right here. Notice that the quadratic one, actually, the population decreases very slightly within that first year, and then second year kind of starts bringing it back up. And right here, we just got to find this slope for species B. And then species A, we're going to find a slope as well where we do, let's call it A of X instead, because then I know specifically we're talking about that, plugging this in. So for this slope here, slope of this one, we'll do A of 2010 and 2016, A of 6 minus A of 0 over 6 minus 0. Over the course of 6 years, how much did we average in change? So I got to figure out, now A of 0 I know is 100. In year 0, in year 2010, there were 100, the population of the species was 100 things. Now I got to plug in 6 into my calculator for this other guy here. 100 times 1.06, that's a 6% increase, raised to the 6th power. I missed a parenthesis, give me a second. Raised to the 6th power. And we're going to round. We're going to round, listen, I'm going to write a rounded value, 141.9. It says 0.8519112. I'm not going to round until I get the division answered. Never round early. So I'm going to subtract 100 and then divide by 6. So divide by 6, I get 6.97. Around 6.975, because I don't know what the other number is going to be yet. Change. So around 7, right? They add around 7 fish, deer, people, whatever it is, population change per year. Right? That's an increase. The other one will be an increase as well. But so for this b of x, we're going to take, now these y values we can get here, this is an increase of 25 every y increment, so this must be 75. At year 6, there is a population of 75. At year 0, 2010, there's a population of 50, divided by the 6 years that we're doing there. That's 25 over 6, which is also a value we can round. 4.16 and 6 repeating. So 4.167 pop per year. So the question was, compare the populations by calculating and interpreting. So there's the comparison. Population A has a higher average rate of change. And it's exponential, so I think it's going to take off even more. Species A, species A. Species, let's type it. And it's likely that it would just dominate the rest of the way from there as well. Okay. Number 35, another analyzing relationships. Let's see what's going on this time. This time we have a table where we have to probably make the model, and then the graph where we have to probably make the model. Three charities are holding telethons. Charity A begins with 1 pledge, and the number of pledges triples each hour. This uses Y and T, Y and T. I'm going to call this A of T. I'm going to go ahead and already come up with that model. So begins with 1 pledge, and the number of pledges triples each hour. If T is number of hours, this is our equation, or A of T equals 3 to the T power. That's an exponential model. Charity B is the table that you see there. So for charity B, I'm seeing a constant increase of 12, starting from 12. So B of T, here's A of T. B of T is a y equals mx plus b. The slope is 12. The y-intercept is 12. There's that. So it might start higher than this one, but not for long. Oh, not for long at all. Charity C is on the graph, and that's also exponential. So it's, oh, that might not be exponential. That actually looks quadratic. Charity C, even though it has that curve, you're not seeing the other side of it with the model there. The reason it's probably not exponential I saw was this 0, 0. Let's talk about charity C for a little bit. So T and C of T. Let's look at some of those and see what's going on, because they're also, oh, okay, I see the other ones. So 0, 1, 2, 3. Let's use those ones. We got 0, 4, 16, and 36. I clearly see a quadratic behavior here as well. It's happening. So although this adds 4, 12, and 20, that is a constant increase of another 8 and 8 from before. So constant increase of 8 from both of these. I'm really seeing that vertex at 0, 0. So this really looks like a y equals 8x squared equation. So I'm going to say C of t equals, because here's the thing. If that was adding 8 each time, then adding 8 from here means subtracting 8 this way, which means this would be minus 4. Wait a second. Did I say that right? Minus 4 would, oh, you subtract 4 from what this was, so this is 4 here. Yeah, so that's going to be a vertex at 0, 0. So C of t is 8t squared. 8t squared. So those are our 3 models that we have. I'll write them up here. I'm sure we're going to have to use them. I jumped ahead a little bit, but part A, I jumped ahead a lot. Sorry about that. What type of function represents the number of pledges received by charity A, B, and C? So charity A is exponential. B is linear. And C is quadratic. Okay. Don't need a period. It's not a sentence. Come on, Mr. Evans. Part B. Write the functions. Oh no! Find the average rates of change for each function. Each function for each 1 hour interval. That was each hour, so that works. Okay, so having the functions will definitely help for what I had here. From 0 to 6. So for A of t, let's do for A. Hold on. The slope of A will be 3 to the 6th minus 3 to the 0 over 6 minus 0. I don't know 3 to the 6th. I know 729. I think it's 729. So 729 over 6. I want to make sure. Oh, hold on. 3 to the 0 is 1. So, hold on. 3 to the 0 is 1. So, let me first make sure 3 to the 6 is 729. It is. So, 729 minus 1 over 6. 728 over 6. I don't know if that's divisible by 6. It is not. 121.3 repeating. So find the average rates of change for each function for each 1 hour interval. So this is around 121.3 pledges per hour. On average. Clearly it's increasing over time. It went from 1 to 3 in the first hour. That was 2 pledges per hour. Clearly exponential has a big dominance effect here. Slope of B is 12. That's just what it is. It's 12 pledges per hour. You saw the rate. That's not going to change over time. I'm not going to waste time doing 84 minus 12 over, all that. You'll still get 12. So slope of C, right? That's the whole idea of linear. Average rate of change is slope. That's what it is. So I'm going to use it. The quadratic one I have to use, though. Where's my equation? 8t squared. So slope of C will do 8 times 6 squared minus 8 times 0 squared. That's 0. Over 6 minus 0. So 8 times 6 squared. We have to do 8 times 36. And I'm getting 288. So 288 divided by 6. And I get 48. So 48 pledges per hour on average there. So boom, boom, and boom. Okay. For which function does the average rate of change increase most quickly? Over the course of 6 hours? Charity A. What does this tell you about the numbers of pledges received by the 3 charities? Okay. So, charity A for which function is the average rate of change? Charity A increases most quickly on an average rate of change over the first 6 hours. What does this tell you about the numbers of pledges received by the 3 charities? That they get more based on a higher rate. I'm trying to think of what to say with that. That they... I don't know what to say about that. It is over the course of the same amount of time, so it can tell you who does get the most over that time as well. So charity A will receive the most pledges. I mean, but you see those... Well, I kind of saw the numbers in my calculations, but anyway. Charity A will receive the most pledges. Then charity C. Then charity B. So, over the course of the 6 hours, the first hour, charity B wins. Right? So, it just depends on what you're talking about for it. B charity A over the long term. All right, number 36. Comparing functions. Let X represent the number of years since 1990, and we have this function representing the population of Oak Hill. In 1900, Poplar Grove had a population of 200 people. Oh, sorry, that was not 1990. That was 1900. I was going to say, oh, great. Now we have to go back 90 years. That's for Oak Hill. So I'll remember H for Oak Hill. Poplar Grove. I guess we can use G of X. Poplar Grove had 200 people, increased by 8% per year. So Poplar Grove will be 200 initially in 1900, and an 8% increase is 1.08 raised to that same x power. From 1900 to 1950, which town's population had a greater average rate of change? Probably going to guess the first guy, because the quadratic to exponential. Because they'll say, over time, exponential is going to win. So 1900 to 1950, we got to figure out average rate of change for the first 50 years. So h of 50 minus h of 0 over 50 minus 0. So h of 50, I'm going to go to my calculator for this. I'm going to do 10 times 50 squared. Oh, I had a squared button. Plus 10 times 50, that's 500. Plus 500, which is 26,000. Now, we're going to subtract h of 0. H of 0 is 500. That's the initial population here. I want to make sure that you remember that we could actually exclude the plus 500s from all our calculations if you really want to on those things. But because I just included it in the plus 500, I'm taking out the 500 of the initial amount. And that is what the 500 means initially. And this is over 50. So 26,000 minus 500, and then divide that whole result by 50, and I get a clear, clean 510. So average rate of change for Oak Hill is 510 people per year on average from 1910 to 1950. Now, for Poplar Grove, we're going to do G of 50 minus G of 0 over, again, 50 minus 0. Now, I know G of 0 is 200. That was the initial population. G of 50, however, I got to sneeze probably. Let me try and not talk. No. If I don't talk, then I don't breathe. Okay, this is a rounded number. It kind of has a lot of decimals, so I'm just doing it to that. I'm going to subtract 200 and divide that by 50. Whoops, not raise it to the 50th power. Divide it by 50. And I'm getting about 183.6. Okay. So, people per year from 1900 to 1950. Which town's population had a greater average rate of change? Oak Hill had greater average ROC, rate of change, from 1900 to 1950. That was the quadratic. That's part A. Part B. Which town will eventually have a greater population? Explain. Pleasant Grove. What's it called? Poplar Grove. Poplar Grove will eventually have a greater population. Because it's called Poplar Grove. Because it is modeled by an exponential function. I gotta sneeze. There it is. I have to sip water in a second. Okay, give me a second. Whew, sneeze took me out a little bit. Did I finish that one? I did. All right, part B. Okay. Yeah, exponential functions will win over time. That's what that thing's going to say. I'm not going to graph it, but there it is. Number 37, comparing functions. Same with 36. So 37, comparing functions. Were we comparing functions all before? Oh, analyzing relationships. All right. Let x represent the number of years since 2000. We have this quadratic function here of r of x since 2000, 0.01x squared. Clearly not a Earth gravity question. Is this revenue? What's this? 0.1? plus 1.08. Represents the revenue in millions of dollars of company A. In 2000, company B had a revenue of 2.12 million, and its revenue increased by 0.32 million each year. So this is company A. I really want to call it A of X. I hope you don't mind me doing that because it's just, they're both going to be revenue things. And I just want to do that. This is company B, so sorry about that. Anyway, this next one's linear. It had a revenue of 2.12 million. This is in millions of dollars to begin with. So for this other one, I can put 2.12 million. This is like my y-intercept in the year 2000. That's what it said it had. And then it does 0.32 additional $1 million every year for X number of years. So that linear equation's here. From 2000 to 2015, which company's revenue had a greater average rate of change? Probably this one. We know company B's average rate of change already. It's 0.32 million. Millions of dollars per year. I should probably write that differently. I'll say it again. 0.32 mil per year. All right. Now A, on the other hand, we're going to have to do, because listen, it's linear. That's the average rate of change. For A, we have to do 15 years later, A of 15 minus A of 0 over 15 minus 0. Now, this is where I said the 1.08 I can totally ignore if I want to, because that's going to be how much they actually started with. And keep in mind, the starting value doesn't matter who started with how much. They're asking what had a greater average rate of change. You can start with $200 million. How much are you changing over time? But this 1.08 is negligent on both things if I subtract them. So all I need to figure out is what 0.01 times 15 squared is plus 0.22 times 15. 0.22 times 15. And that's going to be the top part because we add 1.08 and then we subtract it back out. So that's 5.55. And then we divide that by this 15 here. We get 0.37, and that's on the button. So, so Quadratic was winning. 0.37 mil per year. I thought they were going to stick to their guns of, well, the linear is more to start with. No, it's not. Not over the first 15 years, maybe less, sure. That's part A. Part B, which company will eventually have a greater revenue? It already does. Unless I screwed something up, and I could have, unless I screwed something up, company A already does have a greater one. But I think that's just what they're saying. Eventually, company A will have a greater revenue. Oh, this has revenue? Okay, I take it back. Excuse me. The first one they talked about average rate of change. We never answered which one had more or less revenue over that time. So let me answer that separately based off this thing. Company A, in year 2015, their overall revenue, not rate of change, their overall revenue is $6.63 million. Company B, which I did not calculate, has, in year 2015, $6.92 million. So company B has more revenue in 2015. Its average rate of change is not higher, but it has more revenue. Over time, eventually company A will have greater revenue because quadratics dominate over linear equations over time. Okay. So they didn't really have us check on that. They asked for average rate of change, so it was kind of a thing. Let me take care of some sniffles a little more. Okay. All right, number 38. How do you see it? Match each graph with its function. Explain your reasoning. So I have two quadratic graphs in A and D. I got an exponential in C and linear in B. So we can find the things. I don't know what to explain. I do, but just based off the equations, right? The forms. So A, these are different letters. Okay, lowercase a is an upside down quadratic equation. I'm looking for an x squared, but the a value being negative, that's letter D. Equation, graph A, equation D. Graph B is linear. Looking for an mx plus b, that's equation C. I'm just going to call them for what they are. negative quadratic. This is linear. C is exponential, so I'm looking for the exponential equation. That's equation B. Exponential, these are my explanations. And process of elimination, that's how I can say that. A for D, yeah, it's a positive quadratic. Reason, process of elimination. I like how do you see it questions when they're so quick and fast like that. All right. Number 39, reasoning. Explain why the average rate of change of a linear function is constant and the average rate of change of a quadratic or exponential function is not constant. Well, the basic thing behind it, the constant average rate of change of a linear is because it is linear. Like, linear means average rate of change for slope. It's unchanging. It's unchanging. So, whereas the other ones do change over time. They increase more over time and in different ways. So I could say the average rate of change of a linear function is constant because the dependent variable of a linear function increases by the same amount for each constant change of the independent variable. Variable increases, of a linear function, I should say. Of a linear function increases by the same amount for each change in the independent variable. So it's just a constant increase each time. I go up 3, I go over 1. I go up 3, I go over 1. Each time it's that consecutive amount. It's going to happen there. So linear functions have that constant increase. Whereas the dependent variables on the other ones change by a different amount and more so each time. So let's do a different paragraph there. So I'll say, and this is for both of them, the average rate of change, average rate of change of a quadratic or exponential function is not constant because the dependent variable of either changes by a different amount for each constant change. Now, I shouldn't say it's always increasing. Changes, by a different amount for each constant change in the independent variable. So you have to remember that you can have quadratic functions that, first of all, are negative to begin with, but second of all, go down at a part before they go back up. And they can go up by fractional amounts and stuff like that. So it might be less than linear. I shouldn't say they always increase. Exponential functions, like I said, they can progressively grow, but they can also decay. So I shouldn't say they increase over time more. I should just say it's different. It's always different. There is no slope. There's no slope on those ones. All right, let's go to number 40. Critical thinking. In the ordered pairs below, the y values are given in terms of n. I really need a tissue, man. Let me grab a tissue. Give me 1 second here. I'm very sorry. Where's my thing to pause here? 1 second. Okay. In the ordered pairs below, the y values are given in terms of n. Tell whether the ordered pairs represent a linear, an exponential, or a quadratic function. Explain. So I have 1. Hold on. I have 1, comma 3n minus 1. Should I do like a table? Let's do it that way. I don't know if that'll help or not. I'm definitely not going to plot them. I don't know how that would work. But this is like an x and y. This go 1, 2, 3, 4, 5. So 1. Oh, I'm going to need some space here. 2, 3, 4. That's too much space. Okay. 1, 2, 3, 4, 5. Let's do 3n minus 1. 10n plus 2. 26n. Okay. 51n minus 7 and 85n minus 19. Okay, very, very interesting. Okay. Is this linear, exponential, or quadratic? It doesn't change from what we did before. Does this have a constant first difference, a constant second difference, or a constant ratio? I'm not leaning toward the ratio one. I'm not seeing what I'd multiply this by to get that unless there's some sort of binomial that makes it happen, and we haven't done like polynomial division to work that out. So I'm not leaning toward exponential. I want to check on the linear versus quadratic. I don't think it's linear either because this adds 7n and then it kind of doesn't. So I just want to see what's going on from one to the next here. And we'll just kind of take a look each time. So probably going to be quadratic. I mean, this comes from that chapter. So 3n plus 7n. I'm just going to write what the number is. 7n is 10n. Negative 1 plus 3 is 2. From here it goes from, this is a weird question. From 10n to 26n is 16n. From 2 to 0 is negative 2. Yeah. From 26n to 51n is 25n. And from 0 to negative 7 is negative 7. And then from, I'm going to separate these. And then from 51 to 85 is 34. And from negative 7 to negative 19 is negative 12. So there's multiple parts on this. Now we got to check these guys' differences, right? Because these are clearly not the same. Is the second difference the same? And I'm banking on it being the same here. From 7n to 16n is 9n. From 3 to negative 2 is negative 5. Yeah. From 16n to 25n is 9n. From negative 2 to negative 7 is negative 5. From 25n to 34n is 9n. From negative 7 to negative 12 is negative 5. So a constant second difference. So this will be a quadratic function. It has a constant second difference of 9n minus 5. There you go. All right, number 41, using structure. Write a function that has constant second differences of 3. So we've seen, I might have to write some out again because I don't want to find the examples that we've done because I forget if they were in the examples in the lecture portion or what else. We've seen ones with a constant second difference of 2. We've seen it with 8. I forget if we've seen it with 4. I think we've seen it with 4. Let's do what would happen because this is open-ended. I want to look at some to show you what they look like. Y equals 1x squared, y equals, because I think I know the answer, but I want to make sure. Let's look at, because it's not necessarily 3x squared. In fact, I wouldn't count on it. Y equals 1x squared, 2x squared, 3x squared. When it comes to the differences here, right, this is the whole xy thing. As far as tables go, 0, 1, 2, 3, 4. This would be 0, 1, 4, 9, 16 when it's x squared. And that is plus 1, plus 3, plus 5, plus 7, which means these have a constant increase of 2. So this has a constant increase of 2. Hopefully you know what that number means. The second difference. Let's change it to 2x squared. Y equals 2x squared, where it's now doubling those. 2, 8, 18, and 32. And so now these double. But what happens to the constant things here? These double, where you have 2, 6, 10, and 14, which is a constant increase of 4. So 4. Now, quadratics could potentially be tricky, but does that mean right in between these is the constant increase of 3? Let's see how 3 works just to be sure. If it's like a linear proportionality, we can go off that. But since everything's tripling here, then I imagine everything's going to be tripling there as well. So we can probably work right off that to get that answer. Because I think it's 1.5 or 3 halves. So here, let's try and do it with 3x squared, where we have 1 tripled, 4 tripled, 9 tripled, and 16 tripled. That's plus 3, plus 9, plus 15, and plus 21. So that's plus 6, plus 6, plus 6. Yeah, you're tripling whatever's there. This is one of 6. So if this is working in such a way that whatever your a value is, you double it. Notice this a value is 1, this a value is 2, this a value is 4. That means that you double your a value to get your second difference. I'll put D. Second difference of D. So if I got to double my A value to get 3 as my second difference, then my A would have to be 3 over 2 or 1.5. So write a function that has a constant second difference of 3. Y equals 1.5x squared will do. You can make up anything after that as long as it's that 1.5. I believe it's going to have that. I want to be sure of it, so I'm just going to keep it like that. 1.5x squared is my stretch factor. I'm going to use that. That works. I'm not testing it, but I think you can trust it. Okay. Just from patterns. 42. Critical thinking. Is the graph of a set of points enough to determine whether the points represent a linear, exponential, or quadratic function? Justify your answer. Well, we saw one where I really wasn't sure. Remember this one? It was a very zoomed in look. This one here, number 32. It was a very zoomed in look. And listen, I used a line tool to say, it's not quite linear, but I approximated everything there. It really was a small snapshot of what this whole thing was. And you can't even tell quadratic versus, I didn't even test quadratic. I said that function might not apply, but you can't even tell quadratic versus exponential. So no, the graph is the graph of a set of points, and we don't know how many sets of points. I don't think so. On a lot of cases, the very first ones with a big set, oftentimes you can. You often can, but unless it's a small snapshot, but if it's a small snapshot of what could be misconstrued as any of the three, I can't say for certain that a graph, that the graph of a set of points, is enough to determine whether they represent a linear, exponential, or quadratic function. Okay. That's my spiel with it. Obviously, the first sets that they gave us were very complete. They wanted us to get an answer off it, and it seemed to make more sense. The other ones later, they're like, we'll challenge you, right? If they give us 2 points, could be any of them. Could be a circle. Number 43, making an argument. Function P is an exponential function, okay? And function Q is a quadratic function. Your friend says that after about x equals 3, yep, function Q will always have a greater y value than function P. Is your friend correct? Q is a quadratic? No. Function P is going to dominate that thing, dude. No. My friend is not correct. Over time, exponential functions, such as P, end up surpassing function Q, a quadratic. Yeah, it passed it once. Black passed blue, but blue's gonna come right back up to black. It's a second wind thing. It's like hitting NOS at the end, man. A little Fast and Furious reference. Early Fast and Furious. I don't think they've used NOS in a long time, at least not for racing. Number 44. Thought-provoking. Find 3 different patterns in the figure. Determine whether each pattern represents a linear, exponential, or quadratic function. Write a model for each pattern. Well, it looks like a quadratic function to me. When n is 1, I have 1, and then 2 is 4, 3 is 9, 4 is 16. That's straight up quadratic. But that's based off number of tiles. That's based off area. So maybe that's what they mean. Maybe they say find 3 different patterns in the figure. One pattern that I'm seeing in the figures are based off area. So find 3 patterns. One pattern is area, which will be quadratic. And that one looks pretty straightforward. I don't know if I use y or whatever, or f of n. Let's use f of n. F of n equals, looks like n squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So I think that's one of them. I don't see anything here to be exponential. Linear, we could use like width, or height, or whatever. Length, base, whatever. I'll call width. The width of this thing, that would be linear because it goes based on whatever the thing is. It would be like f of n equals. And n equals 1, the width is 1. N equals 2, the width is 2, things like that. So I guess that would work out. Excuse me. Take care of my sniffles after this problem. And then I could say height, I guess, but it's still square, so I want to kind of change it up. I want to have a different model for it. Let's do, like, what's another? I don't know one for I can't think of an exponential one. I apologize. Let's think, let's do, like, perimeter. That would be another length one, right? So perimeter. Perimeter would also be linear. I don't know if you know this about perimeter stuff. It's still one-dimensional when it comes to kind of revealing itself for what it is. The perimeter of this one is 4. And then this is, 2 plus 2 plus 2 plus 2, 2 times 4, 3 times 4, 4 times 4. Whatever n is times 4 is what you get there. So this f of n is going to be 4n. If there's an exponential, I don't see what it is. At least not right now, and I kind of just want to mosey through it. Let me pause before the last question. Whew, I've been in allergy season forever. I don't know what to do with these things, man. Last question, number 45, using tools. The table shows the amount A in billions of dollars United States residents spent on pets or pet-related products and services each year for a 5-year period. So it's increasing over time. Let the year X represent the independent variable. Using technology, find a function that models the data. How did you choose the model? Predict how much residents will spend on pets or pet-related products and services in year 7. It says using technology. It doesn't say use a calculator, I suppose. But if I plotted those, does my calculator, I got to see if my calculator it does linear regression. I got to see if it does exponential and quadratic regression. Give me 1 second here. Let's plot those in a table. Stat edit. Let's do year 1, 2, 3, 4, 5. And 53.1. Whoops. 56.9. 61.8. 65.7 and 67.1. Okay. These calculators can do it. I haven't done these in a long time. These calculators can do, like, is it stat? You can do linear regression. So what I'm going to do, because I can look at these on a graph, but it's probably going to look it's going to probably look like a snapshot like that bike one. So I can do linear regression. What I'm going to do is find the one. Oh, where do I do the correlation coefficient? But that was linear regression. That didn't tell me the correlation. Is this it? Oh, that's natural log regression. There's one that shows me. I probably have to change a stat setting on here. Oh, is it one var stats? I do not remember how to find correlation coefficient. Maybe I have to change a setting on this calculator to show it. I thought this would have showed my R value and stuff. I think I'm supposed to see what R is, what R squared is. Let me pause and find how to change that setting on this calculator if I can. Give me 1 second. Okay, thanks to the power of Google search and YouTube being the search result, it showed me. And this sounded very familiar. I got to go to catalog, and where's D on this option thing? Is that D? I got to go to diagnostic on. I remember the phrase diagnostic on. I don't remember what it was for. Here's the real problem with this. My calculator emulator resets. My calculator emulator resets itself every single time. So I'd have to do this every single time if I want to do it again. Anyway, there we go. So for a linear regression, I'm going to write these numbers down here for number 45. Give me 1 moment. Linear. First of all, this would be y equals, this is ax plus b, that's like mx plus b. So this would be 3.68x plus 49.88 as an equation. R is 0.9734. If you want to know what R means, it's something called a correlation coefficient. The closer the number is to 1 or negative 1, if it's a negative slope, the closer it is to 1 or negative 1, the more your points are a source of best fit to that line. Or your line is a best fit to those points. 0.97 is very strong. It's incredibly strong. But we might have stronger. So I want to check quadratic. Does this have... So I want to know. This is what I want to check. I know how to linear regression. It has quadratic regression, and it has exponential regression. All right, we're going to do all of these ones. Quadratic regression. We can make this equation. Y equals, and I'm writing these ones down. Don't worry about that. Quadratic regression, ax squared plus bx plus c. y equals, I'm going to round this stuff, negative 0.4, I'll use 3 decimal places, 0.414 x squared plus 6.166x. Oh, they use r squared here, plus 46.98. Okay, because that one used 2 decimal places, maybe I'll use 2 decimal places on these. So 0.41x squared plus 0.6 or 6.16x plus 46.98. Okay. Give me a second. I'm doing stuff on this other side. You'll see it all in a second. Now, this one does not have an r. It only has an r squared. Does it have an r? Do I have to scroll down? Nope, just has an r squared. What was the previous one? This r squared is pretty high up. A quadratic's better than the linear. I didn't look at the graphs. R squared. Oh, that was r squared of 0.97. Sorry about that. So the r squared was 0.97 on this one. For the quadratic one, it was 0.9906. So that's winning. That's a better fit, they're telling you. They're telling you a quadratic curve's a better fit than the linear. So I should probably just look at those 3 first. And then the exponential one. Now, if you're wondering how to do this yourself, you can use Desmos for this, I suppose. I might graph this on Desmos later. This r squared is 0.96. I'm going to omit that one. I'm going to give the winner to quadratic. And I'm going to use that equation that I just wrote out here. So that r squared is less. So I'm going to use this one. That equation there. Now, those numbers are rounded. If I want to use more exacting numbers, I could. But it already had a better fit than the other ones. So what do they ask us to do? Predict how much residents will spend on pets or pet-related products and services in year 7. Let's use our quadratic regression thing for year 7. So, f of 7 is negative 0.41 times 7 squared plus 6.16 times 7 plus 46.98. So, I got to type that in the calculator. I kind of want to use those. Is there a way to save this? This is the only part that I don't know. Is there a way for me to save those numbers into an equation right now? I don't know how to. I'm going to use as many numbers as I can here. Those numbers were rounded before. 0.41428.6. All right, times 7 squared. I'll use 6 decimal places where I can. Plus 6.165714 times 7. I don't know how much these numbers will matter. Plus 46.98. They said use technology. All right. So f of 7. Whoa. Oh, did I not do a decimal somewhere? Let's do that again. That's 6 point. What did I do? Oh, I typed a 2. Let's try that again. There we go. 69.83. I'll say 69.8. So around 69.8. What is this about? Billions of dollars spent. Billions of dollars. So $69.8 billion. All right. So that's what I'm using for the quadratic there. Linear would have probably been less because quadratic probably would have dominated. And quadratic's better, or the linear is less approximate and linear would have been, I think linear would have been less. I don't know about the exponential. I kind of ran out on that one. All right, guys, I'm done with this. That ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. I hope all of it was very helpful for you. The latter half of that killed me when it came to time and such. That really crushed us in that last hour there. So, guys, check out anything else if you need to. Leave me a comment if you have any questions, if you have any corrections to make. But thank you so much for watching. Take care. I will see you in the next one.